Okay, we start with a problem. The problem is prove that the de Broglie wavelength of an electron accelerated through a potential difference of v volts is root 150 over v Armstrong. Okay, so this is the question. If an electron is accelerated through a potential difference of v volts, the wavelength, the de Broglie wavelength is root 150 over v Armstrong. It's very easy to do this. Suppose that v is the velocity of the electron. Okay, the velocity acquired by the electron through the acceleration by the potential difference v volts. Then the kinetic energy or the energy acquired by the electron, that is half mv square, that is equal to, we know, EV. E is the charge of the electron, V is the voltage through which the electron is accelerated. Okay, so kinetic energy is equal to EV, and from this we can get the velocity of the electron. The velocity of the electron is root 2 EV by m. Okay, so this is the velocity. The velocity is root 2 EV by m. Then we can calculate the wavelength. We can have the wavelength lambda is equal to h by mv. So that is equal to h by m. V, for v, we are giving root 2 EV by m. And from this we can get h over root 2 m EV. Okay, and when we substitute for the h, m, ev, e, etc., we get this. We are substituting for h, we are substituting for the mass. Okay, we are substituting for the charge of the electron, and we will get root 150 by v Armstrong into 10 raised to minus 10 meter. So that is Armstrong. So root 150 by v Armstrong, which is equal to 12.25, which is 12.25 over root v. Okay, root 150 is 12.25. So 12.25 by root v Armstrong. So we have got the result. So if you accelerate an electron through a potential difference v volts, its de Broglie wavelength is given by this. And you will get shorter wavelengths for larger voltage. So if you increase the voltage, you will be getting shorter and shorter wavelengths. Okay. Now, using this, we are just calculating the de Broglie wavelength of a 10 kilo electron volt electron. Okay, de Broglie wavelength of a 10 kilo electron volt electron. So this is given by the voltage is now directly given 10 kilo electron volt. That is 10 into 10 raised to 3 kilo 10 raised to 3. So 10 into 10 raised to 3, that we substitute. So you get 10 raised to 12.25 over 10 raised to 2. Okay, the voltage is 10 into 10 raised to 3. So when you take root, you will get 10 raised to 2. So 12.25 Armstrong or 1.225 Armstrong. Okay. Now, once this idea is with us that a moving particle or a moving electron has a wave associated with it, and we can control its wavelength. Okay, the wavelength of the de Broglie wave associated with the electron, that can be controlled by varying the voltage, by varying the accelerating voltage. We discuss now the electron microscope. So this electron microscope is an application of the wave nature of the particles. Okay. So before going into that, let's see an optical microscope. An optical microscope, you know, a microscope where light is used to illuminate an object and get a magnified image. Okay, and we use lenses, lens systems, okay, objective lens, like that magnifying lens or projection lens. So such lens systems are used, and we use visible light in optical microscope. Now the wavelength of light that we use to illuminate the object, that is an important factor in the resolution or resolving power of a microscope. Okay, the wavelength of light that we use, that's a very important factor. It determines the resolution or resolving power of a microscope. And actually we can have certain equations which show that shorter wavelengths yield higher resolution. So resolution increases with the decrease in the wavelength. Okay, if we use shorter wavelengths, it will give us higher resolution. So the greatest resolving power in optical microscope, okay, since we need shorter wavelengths, the greatest resolving power in optical microscope requires near ultraviolet, shortest visible wavelength. Okay, near ultraviolet. Now in the case of a good microscope that uses visible light, a resolution of approximately 200 nanometer with a useful magnification of 500x can be achieved. So a light optical microscope, a light microscope or an optical microscope that can get a maximum resolution of 200 nanometer. That means if two lines are 200 nanometer apart, the microscope can clearly differentiate those lines. That is what is meant by resolution. Okay, so the maximum resolution that we can get is 200 nanometer, and the useful magnification, okay, useful magnification that we can get is 500x, that means 500 times. Okay, if we need more magnification at higher resolutions, we need electron microscope. So we go for electron microscope if we need higher resolutions and higher magnification. Okay, so the wave nature of moving electron is the basis of electron microscope. Okay, the wave nature of moving electron, we are using electrons to illuminate the object and get a magnified image of it. So the wave nature of moving electron is the basis of the electron microscope. The first electron microscope was built in 1932. Okay, so the idea is the wavelength of the fast electrons, the wavelengths of the electrons moving fastly in an electron microscope, they are actually shorter than those of the light waves in an optical microscope. Okay, so we have seen that the resolution depends on the wavelength. Shorter wavelengths give more resolution. Electrons in an electron microscope have shorter wavelengths than the visible light. So, the wavelength of the electron can be controlled by varying the voltage. So, an electron microscope can produce sharp images with a very high resolution, at a higher magnification. So this is the basic idea regarding the electron microscope. Electron microscope uses electrons, and these electrons have wavelengths shorter than the visible light, which is used in optical microscope. So it will be giving you higher resolution images at higher magnifications. So see here we have a schematic diagram of electron microscope. What you see on the top is the electron source, which produces electron beam, and we have a magnetic condensing lens, okay, which condenses the beam, and then we have the object, okay, an object is placed in the path of the beam through which the electron beam passes, and the electron beam is then focused by a magnetic objective lens, okay, and there is a projection lens, magnetic projection lens, and we get an image. So here the lens used in optical microscope cannot be used, because what we have here is the electron beam. So what we need is a magnetic lens. So three lenses used are actually magnetic lenses, okay. So the magnetic lenses are actually current carrying coils, okay. Magnetic lenses are current carrying coils which produce magnetic field, okay. As current passes through these coils, they produce magnetic field, and these lenses then can focus the electron beam on a specimen. Now as the electrons pass through the slice, actually we use very thin slice of the specimen, some electrons are absorbed. As they pass through them, some electrons are absorbed and others travel through the substance depending upon the refractive index or density of different parts of the specimen. So depending upon the density, the refractive index of different parts of the specimen, we will get a pattern, okay. The electron beam is, electrons are absorbed at different rates or at different amounts on the different parts of the specimen. It depends on the refractive index or density of the specimen. So depending upon that pattern is formed, the pattern makes a photo micrograph on a fluorescent screen which records the magnified image of the specimen, okay. So this is what is happening. Now to prevent the beam from being scattered, okay, to prevent the electron beam from being scattered from the specimen and thereby blurring the image. When scattering occurs, it may cause blurring of the image. We use a thin specimen, okay. We are using actually a very thin specimen. So we are using a very thin slice of the specimen in the electron microscope. This is in fact called a transmission electron microscope. This is transmission electron microscope because the electron is actually passing through the object. Now for electrons to pass through the object has to be sufficiently thin, okay. So this is actually TEM, transmission electron microscope. Other types of electron microscopes are there. An example is scanning electron microscope, where the scattering of electron beam by the object is used, okay. So the microscope that we saw here is the transmission electron microscope. So what we said here is, to prevent the beam from being scattered, a thin specimen is used and the entire system is evacuated. Actually all these things, electron beam passing through the different coils, everything is evacuated so that we can avoid the scattering of electrons by the air particles. Okay, so this is how an electron microscope, or rather a transmission electron microscope, is working.